NAT traversal. As an alternative to the complexity of placing ALGs and NAT editors in NAT devices, an application may attempt to perform its own NAT traversal. Usually, this involves the application trying to ascertain the external IP address and port numbers that will be used when its traffic passes through a NAT and modifying its protocol operations accordingly. If an application is distributed across network, i.e. has multiple client and servers, some of which are not behind NATs, the servers can be used to shuffle copy data between the clients that connect from behind NATs or enable such clients to discover each other's NAT bindings and possibly facilitate direct communication. Using a server to copy data between clients is usually a last resort option because of the overheads involved and potential for abuse. Consequently, most appropriate attempts to provide for some method that allows direct communication. Direct methods have been popular for peer-to-peer file sharing, games, and communication applications. However, such techniques are often confined to a particular application, meaning that each new distributed application requiring NAT traversal tends to implement its own methods. This can lead to redundancy and interoperability problems, ultimately increasing users' frustration and cost. To combat this situation, a standard approach for handling NAT traversal has been established, and it depends on a collection of several distinct subordinate protocols that we discuss in the following sections. For now, we begin with one of the more robust yet non-standard approaches used by distributed application. We then move on to standardized frameworks for NAT traversal. Pinholes and hole punching. As discussed previously, a NAT typically includes both traffic rewriting and filtering capabilities. When a NAT mapping is established, traffic for a particular application is usually permitted to traverse the NAT in both directions. Such mappings are narrow. They usually apply to a single application for its duration of execution. These types of mapping are called pinholes because they are designed to permit only a certain temporary traffic, i.e. a pair of IP address and port number combinations. Pinholes are usually established and removed dynamically as a consequence of communication between programs. A method that attempts to allow two or more systems, each behind a NAT, to communicate directly using pinholes is called hole punching. It is described for UDP in Section 3.3 of RFC 5128 and for TCP in Section 3.4. To punch a hole, a client contacts a known server using an outgoing connection that establishes a mapping in its local NAT. When another client contacts the same server, the server has connections to each of the clients and knows their external addressing information. It then exchanges the client external addressing information between the clients. Once this information is known, a client can attempt a direct connection to other clients. The popular Skype peer-to-peer application uses this approach and some others. Referring to Figure 7.7, assume client A contacts server S1 followed by client B. S1 will have learned A's and B's external addressing information, IPv4 addresses 192.0.2.201 and 203.0.113.100 respectively. By sending B's information to A and vice versa, A can attempt to contact B directly at its external address and vice versa. Whether this will work depends on the type of NATs that have been deployed. NAT state for the A S1 connection lives in N1 and NAT state for B S1 lives in both N2 and N3. If all NUTs are endpoint independent, this is sufficient for direct connections to be possible. Any other type of NUT will not accept traffic from other than S1 and will thus prohibit direct communication. Said another way, this approach fails if both hosts are behind NUTs with address dependent or address and port dependent mapping behavior. Unilateral self-address fixing, ANSAF. Applications employ a number of methods to determine the address their traffic will use when passed through a NUT. This is called fixing, learning and maintaining the addressing information. There are indirect and direct methods for address fixing. The indirect methods involve inferring a NUT's behavior by exchanging traffic through the NUT. The direct methods involve a direct conversation between the application and the NUT itself using one or more special protocols that are not currently IETF standards. Considerable effort within IETF has gone into development of the indirect methods, and they are widely supported in certain applications, with VoIP applications being the most popular. Some of the direct methods are now supported by some NUTs. These methods also provide for basic configuration of NUTs, so we discuss them later in the context of NUT setup and configuration. Figure 7.7, applications running on clients behind a NUT may require help from a server to engage in direct communication. In hole punching, a server, often specialized for a specific application, provides rendezvous information among clients that first establish NUT state and then perform direct communication. If possible, some applications attempt to fix, determine, and maintain the address and port numbers their traffic will be assigned when passing through a NUT using standard generic protocols. These methods may encounter troubles in certain situations such as environments with multiple levels of NUT. In this example, client A's external address visible at S1 is 192.0.2.201 and client B's is 203.0.113.100. At S2, however, B's external address is 10.0.1.1. An application attempting to fix its address without help from the NUT performs the address fixing in a so-called unilateral fashion. Applications that do so are said to perform unilateral self-address fixing, ANSAF. As the name suggests, such methods are considered to be undesirable in the long run, but a necessary evil for the time being. ANSAF involves a set of heuristics and is not guaranteed to work in all cases, especially because NUT behaviors vary significantly based on vendor and particular circumstance. The behave documents mentioned earlier are aimed at specifying more consistent NUT behavior. If widely adopted, ANSAF methods will work more reliably. In most cases of Internet, ANSAF methods operate in a client or server fashion similar to hole punching, but with added generality. Figure 7.7 illustrates some of the hazards that can arise in this situation. One issue is the lack of a single outside address realm for every NUT. In this example, there are two levels of NUT between client B and server S1. This situation can cause complications. For example, if an application on B wishes to obtain its outside address by using ANSAP with the server, it receives different answers depending on whether it contacts server S1 or S2. Finally, because ANSAP uses servers that are distinct from the NUTs, there is always the possibility that the NUT behavior reported will change over time or become inconsistent with what the ANSAF approach reports. Given the various problems with NUTs and ANSAF, the lab, an elected group of architectural advisors within the IETF, has indicated that ANSAP protocol proposals must include responses to the concerns in their specifications. First, define a limited scope problem that the short-term ANSOP proposal address. Second, define an exit strategy or transition plan. Third, discuss what design decision make the approach brittle. Fourth, identify requirements for long-term sound technical solutions. Fifth, discuss any noted practical issues or experiences known. This is an unusual list of requirements imposed on a protocol specification, but it results from long-standing interoperability problems between different NATs and NAT traversal techniques. Despite all the aforementioned problems, ANSOF methods are commonly used, partly because a wide range of NATs are found in operation today with little consistent behavior. We now look at how these methods are used as building blocks from robust, general-purpose NAT traversal techniques to maximize the chance that communication among systems behind NATs, even between systems across multiple NATs, such as the one illustrated in Figure 7.7, will be possible. Session traversal utilities for NAT STAN. One of the primary workhorses for ANSOF and NAT traversal is called Session Traversal Utilities for NAT STAN. STAN has evolved from a previous version called Simple Tunneling of UDP through NATs, now known as Classic STAN. Classic STAN has been used with VoIP or SIP applications for some time, but has been revised to be a tool that can be used by other protocols for performing NAT traversal. Applications requiring a complete solution for NAT traversal are recommended to begin with other mechanism we discussed in section 7.4.5, i.e., ICE and SIP outbound. These frameworks may make use of STAN in one or more particular ways called STAN usages. Usages may extend the set of basic or more particular ways called STAN usages. Usages may extend the set of basic STAN operations, message types, or error codes defined in RFC 5389. STAN is a relatively simple client-to-server protocol that is able to ascertain the external IP address and port numbers being used on a NAT in most circumstances. It can also keep NAT binding current by using keep alive messages. It requires a cooperating server on the other side of a NAT to be effective, and several public STAN servers are configured with globally reachable IP addresses and are available for use on the internet. The main job of a STAN server is to echo back STAN requests sent to it in a way that allows the client addressing information to be fixed. As with ANSOF methods in general, the approach is not foolproof. However, the attraction of STAN is that it does not require modification of network routers, application protocols, or servers. It requires only that clients implement the STAN request protocol and that at least one STAN server be available in an appropriate location. STAN was envisioned as a temporary measure, as were many standard protocols now in widespread use a decade or more after their creation, until a more sophisticated direct protocol was developed and implemented, or NATs became obsolete because of the adoption of IPv6. STAN operates using UDP, TCP, or TCP with Transport Layer Security, TLS, see Chapter 18. STAN usage specifications define which transport protocols are supported for the particular usage. It uses port 3478 for UDP and TCP and 34794 for TCP or TLS. The STAN-based protocol has two types of transactions: request or response transactions and indication transactions. Indications do not require a response and can be generated by either the client or the server. All messages include a type length, magic cookie with value 0x2112, A442, and a random 96-bit transaction ID. used for matching requests with responses or for debugging. Each message begins with 20 bits and may contain 0 or more attributes. Stun messages types are defined in the context of methods that support a particular stun usage. The various stun parameters, including method and attribute numbers, are maintained by the IANA ISP. Attributes have their own types and can vary in length. The basic stun header, most often located immediately following a UDP transport header in an IP packet, as shown in Figure 7.8. Figure 7.8, stun messages always begin with 20 bits and are usually encapsulated in UDP, although TCP is also allowed. The message type field gives both the method, i.e. binding, as well as class, request, response, error, or success. The transaction ID is a random 96-bit number used to match request with responses or for debugging in the case of indications. Each stun messages can hold 0 or more attributes depending on particular usage of stun. The basic stun header is 20 bytes in length, see Figure 7.8, and the message length field provides for an entire stun message length of 2 raised to 16 minus 1 bytes. The 20-byte header length is not included in the message length field. All the messages are always padded to a multiple of 4 bytes, so this field always has its 2 low-order bits set to 0. Stun messages sent over UDP or IP are supposed to form IP datagrams, less than the path MTU, if known, to avoid fragmentation, see Chapter 10. If not known, the entire datagram length, including IP and UDP headers, and any options should be less than 576 bytes IPv4 or 1280 bytes IPv6. Stun has no provision for cases where a response might exceed the path MTU in the reverse direction, so servers should arrange to use messages of appropriate size. Stun messages are carried over UDP or IP are not reliable, so stun applications are required to implement their own reliability. This is accomplished by resending messages thought to be lost. The retransmission interval is based on the estimated time to send and receive message from the peer, called the round trip time, RTT. RTT computation and setting transmission timers will be a major consideration when we discuss TCP. See Chapter 14. Stun uses a similar approach but with minor modifications to the standard TCP values. See RFC 5389 for more details. Reliability issues for stun over TCP or IP or TCP with TLs or IP are handled by TCP. Multiple pending stun transactions can be supported over TCP-based connections. Stun attributes are encoded in a TLV arrangement, a technique used by several other Internet protocols. The type and length portions of a TLV are each 16 bits and the value portion is variable length up to 64 kilobytes if supported, but padded to the next multiple of 4 bytes. Padding bits may be any value. The same attribute type may appear more than once in the same stun message, although only the first is necessarily processed by a receiver. Attributes with type numbers below 0x8000 are called comprehension required attributes, and the others are called comprehension optional attributes. If a stun agent receives a message containing comprehension required attributes it does not know how to process, it generates an error. Most of the attributes defined to date are comprehension required ISP. RFC 5389 defines a single stun method called binding, which can be used in either request or response or indication transaction for address fixing and keeping NOT bindings current. It also defines 11 attributes given in Table 7.2. Table 7.2. Stan defined in RFC 5389 and sometimes called Stan 2 replaces classic Stan. These 11 attributes may be used by Stan 2 compliant client or server. Name, map address, value 0x0001, purpose or use, contains an address family indicator and a reflexive transport address IPv4 or IPv6. Name, username, value 0x0006, purpose or use, username and password used for message integrity checks up to 513 bytes. Name, message integrity, value 0x0008, purpose or use, message authentication code value on the Stan message, see chapter 18, and RFC 5389. Name, error code, value 0x0009, purpose or use, contains 3-bit errors, class, 8-bit error code value, and variable length textual description of error. Name, unknown attributes, value 0x000A, purpose or use, used with error messages to indicate the unknown attributes, 1 16-bit value per attribute. Name, realm, value 0x2014, purpose or use, indicates the authentication realm name for long-term credentials. Name, nonce, value 0x0015, purpose or use, non-repeated value, optionally carried in request and responses. See chapter 18 to prevent replay attacks. Name, ZOR map address, value 0x0020, purpose or use, ZOR ed version of map address. Name, software, value 0x8022, purpose or use, textual description of the software that sent the message, i.e. manufacturer and version number. Name, alternate server, value 0x8023, purpose or use, provides an alternate IP address for a client to use, encoded as with map address. Name, fingerprint, value 0x8028, purpose or use, CRC32 of message, XORED, with 0x53545544E, must be last attributes if used. Optional. Referring to figure 7.5, a Stan client with addressing information capital X colon small x is often interested in determining capital X1 tick small colon small x1 tick, called the reflexive transport address or map address. A Stan server at capital Y1 colon small y1 includes the reflexive transport address in a map address attribute in a Stan message returned to the client. The map address attribute holds an 8-bit address family field, a 16-bit port number field, and either a 32-bit or 128-bit address field, depending on whether IPv4 or IPv6 is indicated by the address family field, 0x01 for IPv4, 0x02 for IPv6. This attribute is included to remain backward compatible with classic Stan. The more important attribute is the ZOR map address attribute, which holds exactly the same value as the map address attribute, but ZORed with the magic cookie value for IPv4, or a concatenation with the magic cookie and transaction ID values for IPv6. The reason for using ZORed values in this way is to detect and bypass generic ALGs that loop through packets and rewrite whatever IP addresses they find. Such ALGs are very brittle because they may rewrite information that protocols such as Stan require. Experiences has shown that ZORing IP addresses in the packet payload is usually sufficient to bypass such ALGs. A Stan client, including most VoIP devices and soft phone applications such as PJ SUA, is initially configured with the IP addresses or name of one or more Stan servers. It is desirable to use Stan servers that are likely to see the same IP addresses as the peer to which the application ultimately wishes to talk, although that may be difficult to determine. Using stan servers located on the public internet, i.e. stan.ekiga.net, stan.x10.com, num.viagini.ca, is usually adequate. Some servers may be discovered using DNS service SRB records. See Chapter 11. An example stan binding request is given in Figure 7.9. Figure 7.9. A stan binding request. The request contains a 96-bit transaction ID and software attribute that identifies the client making the request. The attribute contains 10 characters, but this value is rounded up to the next multiple of 4, giving an attribute value of 12. The message length of 16 also includes the 4 bytes used to include the attributes type and length. The stan header is not included. The sample stan binding request in Figure 7.9 is initiated from a client. The transaction ID has been selected randomly, and the request is sent to num.viagini.ca with IPv4 addresses 216.146.46.55 and 216.146.46.59, which is both a stan and a turn server. See section 74.4. The request contains the software attribute that identifies the client application. In this case, the request was initiated by pjnath-1.6. This is the pjzipnat helper application included with pjsua. The message length includes 4 bytes for the attribute type and length plus 12 bytes used to hold the attribute. The length of pjnath 1.6 is only 10 bytes, but attributes length are always rounded up to the nearest 4-byte multiple. After passing through a NAT, the response is given and as shown in Figure 7.10. Figure 7.10, a stan binding response containing 4 attributes. The map address and ZOR map attributes contain the server reflexive addressing information. The other attributes are used with an experimental NAT behavior discovery mechanism RFC 5780. The binding response shown in Figure 7.9 gives useful information to the client encoded as a collection of attributes. The map address and ZOR map address attributes indicate that the stan server determined the server reflexive address of 71.134.182.214:33294. The response origin and other address attributes are used by an experimental facility for discovering NAT behavior, RFC 5780. The first gives the communication endpoint used to send the stan message 216.146.46.55:3478, which matches the sending IPv4 address and UDP port number. The second attribute indicates which source IPv4 address and port number 216.146.45.59:3479 would have been used if the client requested change address or change port behavior. This latter attribute is equivalent to now deprecated change address attribute in classic stan. If a change address or port is specified in a request, a cooperating stan server attempts to use different address when responding to the client if possible. Stan can be used to perform address fixing as well as a number of other function call mechanisms, including DNS discovery, a method to redirect to an alternate server, and message integrity exchanges. Mechanisms are selected in the context of a particular stan usage. So in general, they are considered optional stan features. One of the more important mechanisms provides authentication and message integrity. It has 2 forms, the short-term credential mechanism and the long-term credential mechanism. Short-term credentials are intended to last for a single session. The particular duration is defined by the stan usage. Long-term credentials last across sessions. They correspond to a login ID or account. Short-term credentials are often used in particular message exchanges, and long-term credentials are used when some particular resource is to be allocated, i.e. with turn, see section 7.4.4. Passwords are never sent in the clear when they could be intercepted. The short-term credential mechanisms uses the username and message integrity attributes. Both are required on any request. The username gives an indication which credentials are required and allows the message sender to use the appropriate shared password, informing an integrity check on the message. A mock computed on the message contents. See Chapter 18. When using short-term credentials, it is assumed that some form of credential information, i.e. username and password, has been exchanged earlier. The credential is used for forming an integrity check on scanned messages that is encoded in the message integrity attribute. The ability to form a valid message integrity attribute value is an indication that the sender holds current, fresh copy of the appropriate credentials. The long-term credential mechanism ensures freshness in a different way, using a digest challenge. When using this mechanism, a client initially makes a request without any authentication material. The server rejects the request but provides a realm attribute in response. This can be used by the client to determine which credentials is needed to provide adequate authentication, as the client may have credentials for various services, i.e. multiple VoIP accounts. Along with the realm, the server provides a never-used nonce value, which the client uses in forming a subsequent request. This mechanism also uses a message integrity attribute, but its integrity function is computed by including the nonce value. Thus, it is difficult for an eavesdropper that overheard a previous long-term credential exchange to simply relay a validated request, i.e. because the nonce value is different. The use of nonce values in authentication and related concerns are discussed in more detail in Chapter 18. The long-term credential mechanism cannot be used to protect stun indications, as these transactions do not operate as request or response pairs.